Welcome to Ask and Learn.
Okay, so I like this problem. Basically, here you have, again, the same players in the story, a shell, a charge in the middle. However, the shell has a nice property that its density changes as you go outward. So it gets smaller and smaller. So rho equals A over R. And you're given that this charge in the middle is 45 femtocoulombs. And you're given so plot, spoiler alert, I think that's the only one that you actually need, just 2 centimeters. And never too early to convert a number to SI, so 0.02 meters. And the goal is to figure out what A is such that the field is spatially uniform, even though the charge density isn't. And so basically, first we need to solve for the field within here. So we're going to use Gauss's law to do that. I'm going to do that on the next page. Oh, why are there 3? Okay, well, now I'm on 2. Okay, so Gauss's law, I'll redraw the sphere. You want to put your Gaussian surface within here. And so this is, now we're evaluating the electric field at some radius r. So you start with our usual Gauss's law. So E times the integral of E dot dA equals Q enclosed over epsilon naught. And A is, we chose our Gaussian surface nicely such that it was, such that the integral is a constant, so it doesn't change over space. And the integral of dA is just 4 pi r squared. The dot product of E and dA are the same everywhere along our surface. And so, we get this left side, which you've probably seen before. But Q enclosed is a little more complicated because Q is changing in space. So we do need to integrate to figure out that. So I'm going to kind of do this side integral over here. I'll do it in blue because I kind of anticipate a lot of stuff on this page. So Q enclosed is just, in general, it's the integral of the density times a dV volume element. And our density is A over R. Ooh, look at that integral sign. And the element of, like the differential element for spherical coordinates, especially one that's symmetric azimuthally and like with respect to all angles, basically, that's going to be r squared 4 pi dr. So hopefully you've seen that in some kind of calculus class. So that cancels that, and then we can pull our 4 pi out. And the bounds of our integral are from r to a because that's where the charge is. So it's just the integral of r. So the integral of r is r squared over 2. And then we still got this solid angle 4 pi factor hanging out. And we can cancel this 2 with this 4. And we find that Q enclosed is equal to a r squared times pi and 2. Almost forgot. So I'm going to go ahead and put this over here. And we also can't forget about the charge in the one in the middle. So it's just going to be this. Oops, didn't mean to write in blue. I meant to write in black. So I'll call this just Q. Sorry if that's confusing. So Q plus this Q enclosed is this A r squared pi times 2. I'm going to drop that x so it doesn't get so messy. And sorry that 2 looks like shit. Divided by epsilon naught. And algebraically solving for E. And remember, our goal is to get it to be uniform spatially. So we don't want any r squareds in our final answer. And so, yeah, it's this q plus ar squared. Oh, my bad. I actually just evaluated the integral but didn't do the balance, I realized. Let me go back and do that. So that's evaluated from, oh, and it, oops, and it actually starts out at A and ends at R. So here's A to R, and then it's, so I'm going to reorder these in a little more normal way. 2 pi A R squared minus A squared. And so, okay, now I can go back. So that's A. I'm just going to erase this. Goodbye. Okay. So that's 2 pi A R squared minus A squared. Great. And now if you just like look at this, oh yeah, it's all divided by R squared. If there were no Q and there were no A squared, then this would be spatially independent because the R squareds would cancel. But unfortunately they're there, so you can, so we need that sum to add up to 0. So therefore the condition to be met is Q has to be equal in magnitude to 2 pi A little a squared. And so if you solve that for A, for a little semicolon, then you might get what I got, which is A is 1.79 times 10 to the minus 11